Video, we're going to take a look at the domain and range of functions, which is commonly the x and the y values. We've got a couple of topics that we're going to cover, including interval notation. We'll also see set builder notation, and then we're going to go back to those common functions and look at piecewise functions as well. So we want to start by looking at the domain and range for each of the graphs. So the domain is the set of all x's, and the range is the set of all y's for which the function is defined. First of all, when you see graphs like this, I've just graphed these in Desmos, and so they do continue to go up forever. The x's are represented on the horizontal axis and the y's on the vertical axis. And we can see that this has infinitely many points that make up this particular graph. When we're looking for the domain, so we want to do set builder notation. The domain is the set of all x's. So you're going to start it that way. And then this vertical bar here is such that. Some places use a colon, but we're going to use a vertical bar here. So all the x's such that. We want to know which x's are used. Well, as I take a look and I just look at all the x's here that are being used, I'm matching up my graph to the x-axis. I see that it actually matches up everywhere. So this is matching everywhere. So my graph matches with all of the x values. So back to my pen here, I can say that it's the set of all x's for which, it's every single one, right? So we can say like negative infinity is less than x is less than infinity. We can also say, this is just all real numbers, right? So I can use the symbol for all real numbers. I can say or all real numbers. Okay, now let's take a look at that range. Let's erase what we've got here. It's kind of a mess. Now when we look at the range, we're going to do something similar, but we're going to match it up with the y-axis. I'll do green this time. So we're going to match this with the y-axis. So as I'm matching this with the y-axis, I can see that I have values that match starting at 0, but I'm not matching anything below 0. So I'm matching just everything up above there. So there we go. So my range are all the y values starting at 0 and continuing on up. So as I represent these, go here, it's going to be 0 all the way to infinity, right? Or greater than 0. So my range is the set of all y values such that everything greater than or equal to 0. So we're going to say y is greater than or equal to 0. So that's our set builder notation. Let's take a look at the next example. So I'll go back to purple. We're going to match all of our x's. Let's see, this is -2. -1 would be right here. So this is -3. So as I match, I know that I'm starting at a -3, and then I match every single other x value just forever, right? So I'm matching all of my, grab my highlighter, I'm matching all of my x's 3 and greater. So for this one, it's going to be domain, the set of all x's such that x is greater than or equal to -3. Now I want to do the same for the y values. So if I erase all of this, I'm going to match my function up to the y-axis. And as I'm matching it to the y-axis, this one's really similar to the last one. It matches, I'm just really like squishing it on to the y-axis, right? It matches to y values starting at 0. So just like the last one, this is going to match 0 on. Whoops, I did that in purple, but you get the idea. So back to my pen here, my range is the set of all y's such that, always starts that way, greater than or equal to 0. So y is greater than or equal to 0. Okay, so we've got a couple down. The next one. So the next one, this is one of our reciprocal functions. Reciprocal functions, you can think of that kind of as a fraction, right? I've got the x in the denominator, so it's a reciprocal function. It has a domain restriction in it. X cannot be 2. If I put a 2 in, f of 2 would be 1 over 2 minus 2. That'd be 1 over 0 or undefined. When we see that on our graph here, this would be 1, 2. There are no values that match up with 2. If I look at the rest of the graph, I match everything else. Any other x will work, just not that 2. So if I were to highlight it, I would highlight everything up to 2 on either side, but I would skip right over 2. What I really want to do is say that x cannot be equal to 2. So for the domain is the set of all x's such that x can't be 2. So I just put my rule there, x can't be 2. Okay, now let's take a look at the range. So I'll erase all of this stuff. So now the range, now I want to know what y values we're matching up to. I also have, this is called asymptotic behavior, when we come really close to a value, but we never touch it. We also have asymptotic behavior at 0. So I have another boundary at 0. It doesn't matter what you do with this rule, 1 divided by something will never, ever be 0. But I can match it up with every other y value. Every other y value. So I end up with every y value except for 0. So that's going to be like this. So all the y values up above 0, all the y values down below 0, but I'm just skipping 0. So to express that one, x can't be, y can't be 0. Saying one thing, writing the other. Okay, y cannot ever be 0. So my range is the set of all y's such that y can't be 0. Okay, so that's how we can find those from a graph. In our next couple of examples, we're given the formula instead, and we want to use algebra. You are more than welcome, though, to graph these. I'm going to go ahead instead, I'm going to start by graphing x plus 2 in Desmos underneath that square root. Just to remind you that graphing is such a nice way, such a great visual way to take a look at these domains and ranges. So let's go ahead and graph Desmos. So f of x is equal to, now I want the square root. So I'm going to look for that square root symbol. I'm going to go to my keypad here, and it's right there. Great. Okay, the square root of x, I think it was plus 2. Let me check. Yes, x plus 2. I just want the domain, and I can see that I do start at -2, and it matches with every other x value after that. So it looks like we want greater than or equal to -2. So I've started by doing this. Let me go back to purple here. We want interval notation. So x is greater than or equal to -2. As an interval, let me just graph what this was. My x's started at -2 and they continued on forever up to infinity. So in my interval, I want low comma high. So my lowest value is -2. I'm including it, so I want a square bracket. -2, there's not a high value. Okay, so this is low comma high. Square bracket, if you're including it, parenthesis, we never include infinity. It's just like this concept. Okay, -2 to infinity. I was going to show you the algebra as well. I cannot take a square root of a negative number and get a real number back. So for example, the square root of -1 is the imaginary value I. So I'm looking for the domains and ranges in terms of real numbers. So I can do this with the roots in a slightly different algebraic way. I can go ahead and take the radicand, what's inside the root, and I can give myself an inequality. X plus 2 has to be greater than or equal to 0. I can do the square root of 0. I can do the square root of anything bigger than 0, but not negative. And if I just solve this, subtract 2 from both sides, we get x is greater than or equal to -2. So a nice quick way, quicker than graphing it, right? Greater than or equal to -2. The next one we've got is the cube root of x minus 1. I'm going to go ahead and graph this one. Let's just x this guy out. So I've got f of x, you could also type y there, is equal to, now I want the cube root. It's not here. So I'm going to go to my functions, miscellaneous. I'm looking for an nth root. There it is. Okay, so it's going to be the cube root of, I already forgot, is it x minus 1? X minus 1, I'm not sure. Let's check. Oh yeah. Okay, take a look. What do you think the domain is? See how it's matching with every single value. It turns out I can take the cube root of something negative. For example, the cube root of -8 is -2, right? If you check it, -2 cubed is -8. So there are not any restrictions for an odd root. So this could be anything. So it happens to be all real numbers, -infinity to infinity, low comma high, which you can also write as all real numbers. Okay, let's take a look at the next one. In C, I have an even root. This is a square root. So this one's even. So there is a domain restriction. I'm going to do this using some algebra instead of taking the time to graph it. Everything else is not going to give me any kind of a restriction except the square root. I can't let that guy be negative. So I'm going to take my radicand, 6 minus 2x, and it needs to be greater than or equal to 0. So I can go ahead and just start to solve. I'm going to add the 2x to both sides, plus 2x. So 6 is greater than or equal to 2x, divide by 2. 3 is greater than or equal to x. If I flip this guy around, just do a mirror image thing, x is less than or equal to 3. There are no other domain restrictions. There's only a single even root. There's no variables in a denominator, so everything else is going to work for me. Less than or equal to -3. Let's graph that. I'll graph it over here. -3 is here, less than or equal to, so that would be including that guy or less than, which could also be like this. And we're going down to -infinity. So as an interval, the lowest value, anything less than, oh, that's +3. Anything less than +3. So that would go all the way to -infinity, and I would stop at +3. You can check this with Desmos. See if I can remember this one. 3 square root 6 minus 2x. I'm just going to get rid of this. So 3, and then I want square root 6 minus 2x, square root 6 minus 2x, and I think it was plus 1. Okay, so take a look. It is, I mean, it's funky, right? But it's pointing to the left, and it starts there at 3, or I should say it ends there at 3. And if I just kind of work with my zoom, I'm pinching it with my 2 fingers to do this, I can see that it starts at, let me click on that dot, there we go. Starts at 3, or I should say it ends at 3, if you want to think of it that way, but it matches up with every other x. So a great way, domains are so visual, a great way to double check your work. Okay, back to our worksheet. Another way that you can come up with a restriction, so even roots were 1. The other way is with our denominator. So I cannot have a 0 in a denominator. These are really easy to solve. I can either look at it, or I can just say x plus 2 cannot equal 0. Division by 0 is undefined. If I subtract the 2 from both sides, I end up with my restriction. X cannot be -2. If I'm looking to express this in interval notation, it means I'm going to include everything except -2. So there would be like an open circle there. Or I can say I'm going to go from, here comes my interval notation, low comma high, right? I can start at -infinity, so parenthesis -infinity, up to -2, parenthesis, because I'm not including that one, union, so I'm going to join this with the other side. Let me erase this guy, it's in my way. Union, and now let's start on the other side of -2, parenthesis, -2, and now it continues on up to infinity. So that's how we go around a domain restriction. Okay, here's another one. Can you see that? X squared plus x minus 2. Same story. X squared plus x minus 2 cannot equal 0. I'm going to factor this guy. It's a trinomial, and trinomials typically factor, if they're going to, into 2 binomials. To get to x squared, I need an x times an x. To get to that -2, I need a 2 times a 1. One of them needs to be negative. So I want a +1 in the middle. So I'm going to put a plus there and a minus there. You can multiply that back out to make sure, but what you've ended up with are 2 different factors. X plus 2 cannot be 0, which means x can't be -2, and x minus 1 can't be 0, which means x cannot equal 1. So on our number line here, we need to skip over -2, and we need to skip over 1. Everybody else is included, negative infinity on. Circle, circle. So I'm going to have 3 intervals here. Let's deal with this guy first. It's going to be parenthesis negative infinity to -2, but I'm not including -2. I skip right over it. Then I'm going to do my middle interval, -2 to 1, union, last interval, 1 to infinity. And again, right, you could always graph this guy. Okay, F. F has both restrictions in it. So we do have a restriction in the denominator. I can look at that one. X can't be 4. X cannot be 4. That would give me 0 in my denominator. For the square root, it's even. So I know that x plus 4 needs to be greater than or equal to 0. I can't have any negatives. So x needs to be greater than or equal to -4 if I solve that one. I need to incorporate both of these. Let's put this onto a number line. I know that I can't include 4. We'll put 4 right here. Let's put an open circle around it. But I can have everything greater than or equal to -4. I'm just going to put -4 here, closed circle. Everything greater than or equal, but I need to skip over 4. And then all the way to infinity here. So this gives me 2 different pieces to my interval. So I can go from -4, I'm including that one, -4 to 4, parenthesis, union. Now let's do the second piece. Skipping over 4, and I go all the way up to infinity, 4 comma infinity. Remember, for those, you can always graph those to double check to make sure that your domains match what you're looking at on the graph. Now we're going to be starting with the graph. We're going to state the domain and range for each of these functions. We're given the functions, which is really nice. I'm going to go ahead and start with the domain. Where am I matching up? I'm matching up with every single x going up to 1. So I can go ahead and grab on my x-axis everything up to 1. We're going to express this as an interval. So for the x's, negative infinity, low comma high, up to, we're including 1. So I want a square bracket there at 1. Next, for the range, those are the y values. I am matching up these y values at 0, and then I'm matching a y value for everything else above 0. So that's going to grab everything, whoops, it's supposed to be green, but you get the idea, everything there. So I want 0 all the way up. Remember, low comma high. So low is 0, high is infinity. So we're going to include 0, 0 comma infinity. Okay, this one, we're going to start at 1. Whoops, I want purple. So I'm going to start at 1, but I'm not including it. And then I include everybody up to 2. Okay, so my low is 1, but I'm not including it. High is 2, and I do include it with a square bracket. Now let's match to the x-axis. The y-axis for the range. Not very exciting. It only matches to the number 3. So the range is just the number 3. You could write it in interval notation like this, 3 to 3. You could also write it in set notation like this, or just the number 3. Okay, couple more. So the domain and range on these, let's go to purple. I noticed that the first x that I match with, let's see, that should be purple. The first x that I match with is this -3, and I am including it. And then the last x that I match with is this 2, which I'm not including. So as I write this one as an interval, square bracket, -3 comma 2 parenthesis. Well, I have my purple pen. Let's do the domain on this last one as well. I start matching with an x of 5, which is included, and I stop with a 3, which is not included. So this is going to be low is -5, square bracket to include, up to 3 is my high, parenthesis to not include. And then we've got the range. So let's go ahead and switch over to green. So my range are what I'm matching with the y values. So now matching this up, I'm matching all of my y values up to that point at 4. So my low value is -5, and my high value, you can't see it anymore because I wrote over it, is 4, and I'm including everything else in between. So low is -5, which I'm including, comma, high is 4, also including square bracket. The last one. So I do match with a point at 0, and then everything else. And you'll notice that on one side, this one right here is not included. So I would do an open circle if I was matching that guy. But if I match this guy, it fills the circle in. So it's a little bit tricky, but I do end up including both my low value of 0 and my high value of 2. So square bracket, 0, comma, 2. So I want to just do a really brief overview here. We've got some of our common functions, our toolkit functions. I want to start by talking about these polynomial functions. This one's included also. These polynomial functions have domain all real numbers, every single one of them. Same is true with the absolute value. Same is true with this constant horizontal line function. So that means I can just make up some polynomial function. G of x is equal to 5x cubed minus 2x plus 1. It's a polynomial, which means that its domain is all real numbers. So it makes really quick work of the domain if you can recognize this group of common functions. The domain restrictions show up when you've got either an even root, which would be a square root, which I don't have here. Let me draw it. So an even root, or one of these reciprocal functions. This first one is 1 over x. The second one is 1 over x squared. So I can just make up something. If I do a fourth root of x minus 5, I know that's going to have a domain restriction. If I have something like 1 over x squared plus 7, I know that would have a domain restriction. Actually, that one wouldn't. Let me do minus. There. So that one would have a domain restriction. So any of these reciprocal functions, variables in a denominator have domain restrictions, and any even roots have domain restrictions. Okay, finally, we've got some piecewise functions. Let's just go through these, just remembering to evaluate these differently. I'm going to go ahead and draw this one sort of on a number line. So if I'm up to 2, so here's 2. So up to 2, I'm going to use the function x squared. And then for 2 on, I'm going to use the function 3x plus 1, or I should say beyond 2. So if I'm doing f of 1 lands me right here. So there's 1, and I am in less than or equal to 2. So we've got functions defined on pieces of the domain. So for f of 1, I'm going to square it. 1 squared is 1. F of 2 also lands here. So it is in the x squared. So that's going to be 2 squared, which is 4. Okay, so for the next one, anything less than -1, I'm going to use the first piece of the function. Anything greater than or equal, I'm going to use the second piece. So for this first one, 0 is not, let's see, 0 is greater than -1. So I'm going to use the second piece, which is just x. So g of 0 is 0. G of -1 is greater than or equal to -1. So g of -1 is -1. So we're evaluating based on where we are in that domain.